We're heading for part 2. We're heading for part 2 for learning the intricacies of WebAssembly and how are we going live streaming. All right, so I think we're ready. We're going to continue on learning more of the intricacies of WebAssembly. And last time I was searching about WebAssembly text format, which I had no idea that there was like a text variant of WebAssembly, but it makes a lot of sense. So it's basically kind of the human readable way that we can actually use to understand how the program works. And I think that the book is going to dive deep into it. And which, by the way, wait, give me a second, because I think the Twitch chat may be a little bit off the gate. And give me a second. Come on, paste. All right. And here we go. So we were seeing this diagram, this entire diagram, and I was kind of studying a little bit. We got the web API. This is like, so it comes here, an atomic model of WebAssembly. Things are in gray are not covered in this book. Oh, so that's even amazing. So the text format is something that we can actually go in and dive deeper for in our end and see much more about it. So I'm going to go through the MDN document, and we're going to dive deeper into what is the WebAssembly text format. I'm going to zoom a little bit so you guys can see it. And we got the S expressions. I'm just going to start from the beginning. Understanding WebAssembly text format. To enable WebAssembly to be read and edited by humans, there is a textual representation of the WASM binary format. This is an intermediate form designed to be displayed in text editors, browser developer tools, and other similar environments. This article explains how the text format works in terms of its raw syntax and how it relates to the underlying bytecode it represents and the wrapper objects that represent WASM in JavaScript. So basically what it's saying is that this is how we're supposed to actually read it. I don't know what is WASM text, so let's see more about it. I love to skim through things. So apparently there's the module, memory one, and function. What? Remember that I have no idea about low-level programming stuff. I'm currently like trying to dive in and see how things actually work. I know very little about binary, barely any binary. And so this is like talking Chinese to me right now. Adding functionality to your module. Signature and parameters. Getting and setting locals and parameters. Stack machines, our first function body. Module func param I32 param result I32. Okay, I think that we can read this, right? This is a module that you define, so it's self-encapsulating. Then this is a function, which apparently the function is nameless, since we have no idea what the function is. But we got a param that we define over here, the type of the parameter, and apparently we have two parameters. The left-hand side, I'm going to suppose that's what LHS stand for, and the RHS for right-hand side. And this is the result. And they're trying to add two numbers. So I'm thinking, exploring fundamentals, one advanced feature, calling function from other function in the same module. Oh, there you go. That's how you name the function. So you can call getAnswer with a $sign, func export getAnswer +1, result I32. Okay. In this example, you'll notice an export getAnswer +1 section. Declared just after the func statement in the second function. This is a shorthand way of declaring that we want to export this function and defining the name we want to export it as. Okay. This is functionally equivalent to include a separate function statement outside the function elsewhere in the module in the same manner as we did before. And we got this example. The JavaScript code to call our above module looks like so. WebAssembly instantiate streaming. From our previous stream, we saw that instantiate streaming is like the successor of instantiate because it instantiates the WASM module all in a single call. We also saw that the browser actually parses the WASM bytecode into a native module. So it's actually doing it way more efficient than a traditional instantiate, because apparently that what it used to do is that it worked in blocks or in different sections, and now it's doing it everything once. WebAssembly on instantiate streaming, fetch call WASM. Oh, I like this inline way of calling things. Then object. Oh, you need to export to getAnswer +1. Oh, that's pretty cool. Okay. So this is very raw, actually. Import console log func log param I32. Export logit. Oh, what is import? Has a two-level namespace, so the import statement here imports the log function from the console module. You can also see that the exported logit function calls the imported function using the call instruction we introduced above. Imported functions are just like normal functions. They have a signature that WebAssembly Yeah, I wonder how many modules do we have available. That's one question. Imported functions are just like normal functions. They have a signature that WebAssembly validation checks statically. They're given an index and can be named and called. Okay, so we're gonna make this a little bit more interesting. I'm gonna open ChatGPT and I'm gonna use this one. I'm gonna say you're going to reference this URL for any questions. You're also going to be an expert in WebAssembly, and your task is to teach me about WebAssembly topics. I'm going to ask you questions, and I want you to answer me in a concise yet very insightful manner. Are you ready? Dun, 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 dun. This "Are you ready" form, I actually got it from a digital writing course from Ship30 430. If you don't know about Nicole School or Jesus. And Dickie Bush. Oh my god. Nicholas Cole and Dickie Bush, they are very good to check out. You learn a lot of things. My first question is, what are the modules available to what? While this loads, we can actually see this. We have already seen JavaScript calling WebAssembly functions. But what about WebAssembly calling JavaScript functions? WebAssembly doesn't have any built-in knowledge of JavaScript, but it does have a general way to import functions that can accept either JavaScript or WASM functions. Oh, let's look at an example. Import console. Oh, I didn't read this part. So, import console, there is really just one module. What you probably care about is what can go inside a module. Now, the main building blocks module fields you'll see in what. Type declares reusable function signatures. Import declare things this module needs from the outside world. Okay. JavaScript, other wasm. Functions, memories, tables, globals. Func, actual functions, parameters, results, locals, and instruction body. Memory, global, export, start, exposes functions, memory, table, globals to the outside. Okay, start optional main function that runs automatically when the module is instantiated. That's what we were talking about earlier on. Elem initializes entries in a table from the function to give it the indices. So in what you always have, module, any number of, type, import, func, table, memory, global, export. Okay. If we want to take a tiny .1 and annotate of those so you can see them in context. Not yet, boy. JavaScript functions have no notion of signature. So any JavaScript function can be passed regardless of the import's declared signature. Once a module declares an import, the caller of WebAssembly.instantiate must pass an import object that has the corresponding properties. You know, the more that you read about WebAssembly, the more you realize that it's just another way of communicating with JavaScript. So there's no way in this world that JavaScript is going anywhere. And in fact, any programming language that has been how do you call this? It's already being used in the wild and it's deployed and appropriated on several production instances. It's probably not gonna go anywhere. Like JavaScript's here for stay as the same way as COBOL is still around. The same thing is gonna happen with Java, C#, Ruby, Rust, Go. They're not gonna go away. So I think that now how relevant they become on newer software, that's another thing. But I think that JavaScript is gonna become it's gonna stay mainstream for a very long time. Especially since all the LLM tools, it's the default language that it actually uses, and Python as well. Const import object console log WebAssembly instantiate streaming. Okay. Fetch logger wasm import object. Oh, you pass the object. I wonder how does that work? Do you actually pass it by In the following excerpt, does the import object gets passed by reference, or how does it work? Let's see. It's thinking, checking MDNS. OJS, right. Why really works? Okay. So it says effectively passed by reference to the engine. Because I think, and you guys can't correct me if I'm wrong, but I think that there's some sort of copy when it comes to, for example, workers, that even if you're passing an object, which you traditionally send, I wanna see something. Wait, workers pass by reference or copied JavaScript. Copying a reference. This may be non-server optimization reply. It's represented by the get it done. No. You can run whatever code. Yeah, both sides send their messages in the post message method. I do have a question. When you use the post message to communicate with a worker, how does the value is copied to the worker, or can it be passed by reference? Because that's where the UINT and the shared array buffer comes into place. Copy via structured clone. When you do post message, the browser uses a structured clone algorithm and creates a deep copy on the other side. Yeah, that's it. Get its own copy. If the worker does that does not change the array buffer. Exactly. Similar low-level things. Right. It's neutered. Interesting. That's a very interesting word. I've never heard about it. This is zero copy or close as the engine can get, but still not shared reference. Ownership just moves from one side to the other. Interesting. I think this is because they want to avoid racing conditions, which makes it really hard. Really hard, especially since JavaScript is a single-threaded language. I wouldn't imagine how hard would it be. And based on on the event loop, try to sync two things together. And that's why they just send yep, they move the ownership by reference ship. Most see changes. Both threads have views. Writes in one are visible to the other. You need atomics to coordinate it safely. Fast by reference with workers. Using a shared array buffer as the backing memory for wasm modules, so multiple workers or main plus worker. No, I think we're getting a little bit out of the concept, but I didn't want to go really deep into this. I want to go back to the book. So okay, here we are back to the book, and it says, at the center of the WebAssembly universe is the WebAssembly core specification. It defines several things. We got the execution model, which is the instruction set and a formal definition of how the instructions are interpreted. The binary module format, the .wasm, which is the primary way of packaging and distributing WebAssembly. So we got the execution model, which I still have no idea what it is. Yeah, the system interface WASI. Okay. The binary module format. Okay, that I know. The validation rules, what it means for a module to be well formed. Okay. Textual format, which was the thing that we were talking about, which offers a human readable way of defining modules. Okay. This book covers the first three topics: the execution model, the binary module format, and the validation rules. Most of the focus is on the instruction set and execution model. since we think these are the most interesting aspects. We also touch on validation because that's a critical aspect of the WebAssembly safety model. We do not cover the textual format. This is arguably not really a core aspect at all, since most producers and consumers don't need to support it. Oh, that's pretty interesting. The WebAssembly core specification defines an inside view of a WASM implementation, but there are many things it does not define. How are modules instantiated, and how are inputs provided, and how are exports accessed. This kind of details are provided by the host environment and are covered by different specifications. For example, web browsers and JavaScript runtimes like Node implement the WebAssembly JavaScript interface as the WebAssembly Web API. Since this book uses JavaScript, we'll cover large parts of those specifications as well. For non-browser runtimes, there are efforts to specify APIs that cover things like file system, networking. This is known as the WebAssembly System Interface, or WASI. Due to the large scope and the fact that the proposal is still in flux, it's not covered in this book. See how it's going? I think this has gotten way bigger than last time. Yeah, it's only like 0.3. And we're on the roadmap. This is gonna take like a decade. August 2025, we suspect around November 2025. This takes a long time to get things right. Oh, they're planning actually on release candidate like on post 2026. Oh, like for next year. Interesting. Interesting. To really understand what WebAssembly is and what makes it special, you need to understand the low-level details. In this book, we use a hands-on approach to teach you the core of WebAssembly, the instruction set, and the module format. Since WebAssembly is primarily a compilation target, we think the best way to learn the details is by writing a compiler. Really? This is awesome. In this book, you'll create a compiler that compiles a simple programming language down to WebAssembly. The focus is on WebAssembly, not the finer details of parsing. So the compiler is built with a user-friendly parsing toolkit. Let's see. Never heard about a JavaScript library for building parsers, interpreters, compilers, and more. Toolkit consisting of library and domain-specific language. You can use it to parse custom file formats. Special grammars, which are all the you need is included in the text, along with the instruction of running it. Nothing is left as an exercise for the reader. We expect that most readers will build up the code step by step in the order presented in this book, but full code for each chapter is also available on GitHub. Nice. This book is very much centered around code, so before you dive into technical content, it's for understanding our thought process and how the code is tends to be used. You'll get the most out of the book if you have the text editor or IDE opening at the same time. Our intention is that most readers will type out or copy and paste the code and run it themselves. It's open source, provided my 2 license guys. This is amazing. We build up a source code for a single source file. Okay. Create belong. Okay, in each chapter, we build up the source code for a single source file. Okay. So basically, chapter 1 will contain all of those chapter 1. Chapter 2 will build on top of chapter 1, and it will just continue onwards. Okay. Yeah, it's like a way of creating like a checkpoint. So in here it says the function variable will create belong to a single namespace which will build over the course of the book. Each source file depends on the source from the previous chapter, so the chapters end with exports and the following chapter begins by importing anything it needs from the previous chapter. Below is an example of a code snippet. Notice that it has a tab with a chapter file name. If you're reading the online version of the book, you also see a copy button in the right corner. Copy button. Oh, in the top right corner. Yeah. Okay. That are just used for explanatory purposes and aren't intended to be. You can organize the blog. They don't have a tab. The chapter file, so they don't have this. Okay. Checkpoint. Checkpoint is a point where the code is in a consistent state. if you are following along by cutting and pasting or typing a code parses that the text pass, damn, this is actually a lot of work. Copy up to here. Does this work? Oh. Okay. Oh. Nice. Node.js, you like to run the code locally. First mention no install. We recommend starting with the project template that we provide. You can set up the project. Let me see, because I have no idea if there are people around here. Okay, now we got it. With the template that we provide, you can set up your project by running the following command. Okay, so I'm going to come in here. I'm going to come in Finder. I'm going to go to Programming. Right click, Services. New warp tab in here. I'm going to close this. And we're going to run npm create. Okay, I'm just gonna create mkdir, wasm-port. So this is gonna create. Yep. Yeah. Let me see. Okay, so now I can. So now I can wasm roundup 1 to wasm roundup. I thought. Mm-hmm. Okay, clear. Okay, I'm going to open this in VS Code. Oh, but you got everything in here. Oh, okay. Assert, okay. Okay, this is good. So, you don't have Node installed. You can always come finish stack with testing in JavaScript. You typically, for example, in Python, embedding tested the same source file that going being tested. We like that approach because it's naively right on plain changes things in the same model will run into small problems. Chapter imports the previous one, so and one because of that running, including the ones in chapter 1. Make test function. We'll use it in chapter like this. Start with the project template we mentioned in the previous section. There's nothing more to do. In case you're not starting with a template, the implementation is below. There's no need to study it closely, but we've provided some explanation in case you're curious. So let me see. I don't know how this works. Probably see as you follow along with the code in the book, you may find yourself needing to debug some generated wasm. What the best tool of doing that is Yuri the Landix Wasm Code Explorer. Okay. Oh wow. So the purple thing. No. Memory. So memories in blue. Exports. Imports. We also recommend installing the WebAssembly binary toolkit tools. 4 days ago. Oh wow. Wabi. We pronounce it Wabi. It's a suite of tools for WebAssembly, including What-to-Wasm, binary format. Oh, this is damn. It's readable C-like syntax. What the sugar. Wasm to C. Wasm to JSON. Wasm stats. Spec test inner. Online demos. What to Wasm. Add to. Okay. Building on using the top level makefile. Okay. Okay, this is gonna be later on, but it's very good. It's like one of those things that you have no idea what they're using for. They're used for, and then you slowly get to learn them as it goes. As you learn in the introduction, WebAssembly can be described in multiple ways, depending on the perspective we take. But its most tangible representation is a file with the .wasm extension, module encoded in its binary format. Ultimately, our goal in this book is to build a small compiler that compiles a simple programming language to WebAssembly. To do that, we will need to know how to produce a libass-wasm module. In this chapter, we're going to take a close look at the WebAssembly module binary format. Okay. The following at the top of chapter 01.js. And we're going to come in here. I'm going to make my editor window a little bit bigger. Goodbye, agents. I don't need you this time. I'm also going to make this a little bit smaller. I'm going to make it here to the left, so everybody can see it. Make this a little bit, okay. Okay, this works. And the snippet is explained in about the code, so you may want to read that if you haven't already. I have not read that. And then the technical content, structure and mechanics, and it's... Oh, wait. That's what we actually read. To make sure everything is working, try adding a basic test. Okay. Test. Whoop. Activating extensions. Why are you activating extensions? That should be instantaneous. What is going on? I think I'm gonna go with NeoVim. Give me a second. Give me a second because this is not working. And Vim. Oh right, I forgot. Let me see. I'm here in Warp. And Vim. Chapter 1. Okay. Explorer tree. Okay. So we're gonna come in here. Test. Setup. Gonna come in here. Assert. True. So I... Then we can do node chapter 01.js. Oh, wait. No, I quit it. It's like, I'm just so used to this. Okay. I have very little NeoVim experience, so I also need to come in here. So it says no chapter 1. Oh wow, it does work. When you put the screen name on the command line, it will always execute the task contained within that file. Even if the tabs option was not used. Interesting. Should see that the test is passing. Okay, but then compile like a huge and complex task. Here we are, where we wanted to come. As with any other project, one of the hardest things is figuring out where to start. Good way to get started is to ask, what is the minimum viable WebAssembly compiler, or more generally, what's the simplest compiler? The simplest compiler is probably the one that compiles the simplest programming language, but then, what is the simplest programming language? We see a compiler as a function that takes text, source code as input, and returns a runnable program as output. Then the simplest programming language is a language that only takes an empty string and input as input and generates a valid program. Does nothing. So basically, I'm gonna pass something empty and just gonna generate a program. And let's call that programming language voidlang. Its compiler will be a very simple WebAssembly compiler generating the simplest possible WebAssembly module. Okay, so we're gonna create a new programming language. That's freaking awesome. The most common way of handling binary data in JavaScript is typed arrays. These APIs provide array-like interfaces for reading and writing an underlying chunk of memory. So something very important to note is that arrays in JavaScript aren't exactly arrays, because that's something that I never understood until I went to and began like learning C#. After seriously dealing with programming in general, like for 8 years with PHP, with crude basic PHP and some JavaScript, like with toy projects. And the reason is that arrays are fixed of length. What we get to see in here are more dynamic types. So whenever you append to an array or you reduce it, JavaScript underneath, it's actually expanding its memory allocation. So arrays are always like fixed in length. The very difference is that they are contiguous. They're contiguous. That means that when in the memory, in how memory is structured, they are like positioned one next to the other. And since they are kind of like dynamic, they are not exactly arrays by all that means. But in here, a uint8 array let us manipulate the individual bytes much like an array of number. Unit is short for unsigned integer. It's very important. And the 8 means that each entry is 8 bits. Here's an example. New uint8 array 2, an array of 2 bytes. R0 equals 5, R1 equals 7. And R0 plus R1 prints 12. A byte can only hold one of 256, 2 to the 8 possible values, which means that every entry must be in the range of 0 to 255. What happens if we try to assign a large number? It doesn't happen. Okay, we need to be very careful about that. I think that really what happens is that once it reaches to the 256 point, it actually starts over again. So that's why it's actually printing like 44. And we can actually how do you say this, proof? You can say const a new int 8 array. We're just gonna make it 1. It's okay. Wait. Oh. Right. My bad. We're gonna make it 1. I'm gonna say a0, and we're gonna make it again 301. It should be 45. And the reason is 256, 300, 1 minus 256 equals 45. That's the reason. And if we actually come here and say const b, new uint8 array. Actually, I think that we can redefine it in Chromium browsers. uint32 array or 16 array. If we actually do this in again, that's gonna be fine. That's gonna be fine. Note that I'm redefining the constant because I remember that in DevTools you could actually do this. It's one of like those tips. Hexadecimal. Sometimes helpful to use the hexadecimal base 16 representation for binary data. In hexadecimal or hex, a byte can always be represented by 2 characters. From 0 to 255 FF. Okay. This property makes it convenient for fixed width layouts in a monospace typeface. Okay, this property makes it convenient for fixed layout with layouts in a monospace. Here's an array of 8 bytes. I think there should be more differences. 0, 1, 2, 3, 255, da, 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 da. Using hex, we could show the contents of the array like this. F, E, A, B, C, D, E, F. Give me a second because I never understood how hexadecimal actually works. So I want you to guys take some time with me as I'm trying to learn something. I want to see if this is like the right intuition. Oh, right, I forgot. We're here. So it says 0 to 255. 0, 1, 2, 3, 4, 6, 7, 8, and 9. A, B, C, D, E, F, G, F. First 6. So here are 10, and here are 6. And possibly 60. You're an expert in hex. Can you explain to me how hex works and how are they constructed? It's also common to use hex to imply that the value shouldn't be interpreted as a number. For example, an ASCII new line character can be represented in different ways. 10 in decimal, 0x0a, or 0xa in hexadecimal. Use of different counting systems is very friendly to binary. 0 to 9 and each position in a power of 10. A, B, C, D, E, F. Oh, okay. So that's why we are. AF represent decimal values 10 to 15. Each position is a power of 16. For example, 2F16. 2 is in the 16 to 1 place. Okay, F is in the 16th place. 16 0 place. 15. Total 47 in the 10th base. Oh. Okay, of course, because this is in base 16. One hex digit equals 4 bits. Binary is base 2, so each digit is a single bit, 0 or 1. Hex is base 16 equals 2 to the 4, so one hex digit corresponds exactly to 4 bits. Oh. So 0 to F2, 0010 F. For a full byte 8 bits. Got it. This is why bytes, memory addresses, colors, etc. are so often written in hex. Repeated division by 16. Let's convert 419 to hex. 3, the least significant. 60. 1, reminder C. From last to first. 1A3. Same number of. Okay. I'm not understanding it like 100%, but probably get into it. Okay, now we're ready to jump in and implement void lang. I'm gonna get like slowly more intuition about it. Because something I've learned when it comes to like to programming, and I thought that this was my dad. My dad is like a surgeon. He doesn't know anything about this, but he was like one of the early few people back in my country, the Dominican Republic. from getting like computers, and he got a manual that once said that not for you not to learn like try to memorize these things, that it was like through repetition that you get to better understand them. And I've been treating programming like that. It's much better to like dive into an exercise, make small tweaks and changes, and see how they evolve, so you get a much better understanding of how the entire system works. So it says in here, let's create a function that takes the code for a program as input, parses it by checking that it's a valid program. This cases the empty string, returns an array of bytes, which encodes a minimal WebAssembly module. Okay. So takes the code for programs and input, parses it, dun dun dun, an array of bytes. It's a minimal WebAssembly module. Yeah, this is pretty cool that you can like hover over things and then they will show up. So I'm going to delete this. I'm going to come in here, say function compile void lang, say code. Oh, I love the autocompleter here. If code throw new error. Oh, okay. Empty code. No, I'm just gonna leave it like that. Turn uint 8 array from. Oh, I like this. 0, 97, 115, 109, 1, 0, 0, 0. We save. But wait, what are those 8 bytes? That's what I was asking. That we're putting into the uint 8 array. Don't worry, we'll get to that in a moment. First, let's verify that we're indeed producing a valid wasm module. We will use the WebAssembly JavaScript API to instantiate the module. Much like a class in object-oriented programming, a WebAssembly module is a kind of template which can be used to create multiple module instances. Dun dun dun. Let's verify that we're indeed producing a valid wasm module. Compile void line results compile. Okay. All right. Coming here. dd 58. Test compile void lang result compiles WebAssembly object async const instance module await WebAssembly that instantiate compile void lang. Okay. Assert string equal instance of WebAssembly dot instance true. Now copy that. Come here to module instance of. Okay. So let me see. Can I just, I don't know how can I, wait. I can split it. The thing is that I don't remember now how to open a new buffer. Let me see, Explorer, keyboard lazy vim, select grab toggle, buffer key map, split window right. It was like in B. Delete buffers to the right. Split window to the right. No. Nope. I'm telling you, there's a lot of things that I still don't know about NeoVim and LazyVim especially. The thing is that how can I create, debug, file, find, quit, search, UI? Dun 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 dun. Damn, there's a lot of things we can do in here. And toggle scratch buffer, split window, split window below. Oh, there we go. So now I can come in here. Buffer. Oh, so I thought this one deleted the split. Window, delete window. Oh, yeah, okay. Okay. I want to add. Let me see. Edit, focus blocks, clear blocks, AI, drive. Using LazyVim, how can I create a terminal at the bottom of my buffer? Okay, leader, FT. Oh, oh. See. Nice. This was the thing that I was looking for. Okay, awesome. So we're gonna come in here and we're gonna come note and nope. Chapter 01.js. Assert. It's not defined. Assert. Let me see. Buffer. So now I'm gonna come node chapter 1.js. Okay, it worked. This is the first code checkpoint in the book. Right click and open We pass the module byte to instantiate and it returns both the module instance and an object representing the compiled module. Okay. Okay. So I want to say something because this is what I'm gonna do. I know he's going to explain it, but I want to see what happens if I change this. Control \\. How can I navigate use my keyboard between the two buffers? Sometimes I don't know if thinking is the best way. So Control J. Okay, so it uses Vim motions and the control. Okay. Okay, got it. Thank you. Okay, clear. Clear. It actually failed. Expected magic word. Oh, nice. 97. Clear. Oh, nice. And with a magic number. To identify the format. The magic number for WebAssembly module is a string wasm, as encoded as UTF-8. Text encoding is a rabbit hole far too deep for this book. It's a single byte. I remember reading a post in from Go saying how hard it was to actually parse both UTF-8 and ASCII. That's why so many programming languages make it. We think the strings are given, but they are not. So many conversions because there are characters that may have like more than a single byte. So that's why it is crazy. It is crazy manipulating strings at the very low level. There's a lot of things that go into it. So in here, it's enough to know that in both TF-8, each letter in the English alphabet is encoded as a single byte. Since UTF-8 is used for all strings that appear in WebAssembly module, it's worth writing a small helper for converting JavaScript strings to UTF-8. String to bytes. Okay. New text encoder encode S. Interesting. So we're gonna come in here. Dude, I'm sorry. I'm gonna violate this book. And I'm gonna, well, come in here. And I'm gonna say mkdir shared. And I say touch shared utils.js. And I'm gonna come in here. Shared utils. And I'm gonna say export function. I'm sorry. I don't want to write this thing like gazillion times. Const bytes equals new text encoder. Encode S. Never used text encoder in my life. I'm gonna look for it. I generally never go to the docs. Rarely I do that, but since I want to learn more about the things. Code JavaScript use string using UTF-8. Oh. Always return UTF-8. Interesting. So if I come here and say a text encoder. Encode S. Add my chicken. My chicken. Where's my chicken? My chicken. It's not showing up. My chicken is not showing up. Where's my chicken? There we go. My chicken. There we go. There we go. My chicken. Come on, my chicken. Jesus Christ. So it returned a uint8 array. Oh, interesting. And here we have in the book, return array dot from bytes. Okay. It's actually transforming into an array in JavaScript, which we know that it's not an actual array. But okay, so we're gonna come here, right? All right. We use the text encoder interface, which is a built-in node and browser API for converting strings to UTF-8. More convenient for our helper return regular arrays, and we convert to an uint8 array only at the end. I know it. We're learning stuff in here. This is not the most performant thing because we're making a lot of conversions, but I understand this. It's gonna be way better for us to manipulate things. Then we can write ourselves small helper function to produce the magic number. String to bytes. Function magic. Tabs. I still gotta improve my management. Yeah, my import from shared utils.js. And oh man, I forgot. Come on, close it. String to bytes. String to bytes. Okay, 30. Now come here. Function magic. Return string to bytes. So magical 0 ASM. Okay. For the null character code 0. Okay. Interesting. The magic number is followed by a 32-bit integer indicating which version of the WebAssembly module version is used. Currently, the only valid version number is 1, but this may change in the future. Here's what the official specification says. The version of the WebAssembly binary format may increase in the future if the backward incompatible changes have to be made to a format. However, such changes are expected to occur very infrequently, if ever. The binary format is intended to be forward compatible, such that future extension can be made without incrementing its versions. We don't take this for granted. We take this for granted, but the web is entirely backwards compatible. And that is a very huge thing. There are certain deprecations, I understand that, but it's very minimal. Very, very minimal. That's what really happened with the flat map array. That I think it was MooTools that used it. And just for the sake of not breaking it, even if MooTools is not used like today, there are sites that did use it. Sorry. Hey, you're going to be. It's even more surprising that even jQuery version 1 is still used around. In any binary data format, if you want to encode interior values greater than 2255, that is 1 byte, you need to define the byte order. WebAssembly uses what's known as little endian ordering, which means the bytes appear in the opposite order of what you might expect. My God, Indianness. We're going to cover that really quickly, but Indianness is about memory ordering. There is something called like little endian and big endian, right? In which it's like the order in which the memory is stored. One comes from left to right, and the other one is right to left. And that is a concept that I just skim through it. It's not something unless you go like very low end that you work into it. If you've never heard of byte ordering, don't worry, I'll cover it in more detail later in the book. This is awesome. This is what we did with the magic number. Let's add a helper for the version number. Okay. Okay, function. Version. Return 01 0x00 0x00 0. Okay, give me a second. Want to learn more about this. Okay. Encode the WebAssembly version number. Decimal 1000 is the same as 1000. Version bytes 4 bytes, little endian, your version function uses version 1 of the binary format. That's what your compiled void lang returns. Oh! 097 115 109 100. Asm magic in version 1. If you want to write compilable language to use your magic and version helpers, don't worry about it. We're gonna get there. Yeah, that's what I thought we were gonna use. Yeah. Okay. Yep. Bum, 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 bum. Magic. Version. Turn array, we use JavaScript spread syntax. Yeah, we already know that. And as we construct more complex modules, it'll be easy to forget the somewhere. Instead, we can use the built-in flat method on the array to recursively flatten the entire contents. Flat infinity. Oh, that's a very good use of the flat. That's good. That's good. That's actually a very clever way of using flat. That's a very clever way of using flat. No, it's not here. It's here. And infinity. That's okay. Optional parameters specify that the nested array should be flat. We specify depth of infinity to ensure the final result is a flat array of numbers. I don't know what we're gonna do, but it's okay. Void lang is a good start, but you may be thinking that's not even a program, and you're right. The smallest viable WebAssembly module doesn't have something we can run. The closest to running we can do is to create a module instance. Let's extend our compiler to a main module with a function we can call. The smallest step forward is to compile a function that does nothing. A function that takes no arguments, does nothing and returns nothing. Let's call our new language NopeLang. A language whose only valid program is an empty string compiles from a module has a function called main that does nothing and returns nothing. Since JavaScript functions always return a value when calling a WebAssembly function that returns nothing from JavaScript, will return undefined. And this is the smallest step possible, requires the interaction of 4 new WebAssembly module sections. Oh wow. After the preamble, which is the magic number and the version number, a WebAssembly module consists of 0 or more sections. In other words, every section is optional. An omitted section is treated as if the section was there but empty. In voidlang, we had no functions, so we could omit every section. To us humans, a function may be a thing defined in a single place, but WebAssembly expects a function definition to be split into 3 sections. The type section contains the function's type signature. The function section is where the function is declared, and the code section contains the body of the function with the executable instructions. Here it's about saving space. If multiple functions share the same signature, they can all refer to the same entry in section. Inside the module, the function is referred to by its index into its section, for example, when calling or exporting the function. Yes, a function is split into at least 3 parts. So let me read this again. Code section contains the body of the function with executable instruction. The function section is where the function is declared. The split between the code section and the function section is to enable parallel. Okay. Okay. This is interesting. Turning code from a human readable format to a computer readable format. And WebAssembly wants functions split into multiple sections. Notice what didn't mention where the name of the function goes. This is what we had at previously. This is because internally WebAssembly only refers to functions by index. Oh, the function section and the code section must be the same length. Wait, the function section and the code section appears as index 2 in both sections. Interesting. We only give names to functions when we export them in the module's public API. Section basics. The sections in a WebAssembly module have a common structure consisting of 3 parts. The section identifier is a single. Okay, so here we are. Okay, in a section. The section identifier is a single byte that specifies which section is being defined. For example, the type section has the ID 1 and the function section has the ID 3. A size field which represents the size of the contents, the section payload in bytes. Jesus Christ. The contents of the section. I think that we specify the size just because it makes it very convenient to when it comes to parsing. I think that's why we add it. And we enforce this to make it much more efficient. I think that's what we're doing because there's no magic into it. The contents of the section, the structure of this can vary based on the type of the section. Well, most of them are structured as a list of 0 or more entries. To save space, all integers in WebAssembly module are encoded with a variable length encoding. You try to encode the value using only 1 byte. If it doesn't fit, we'll try 2, then 3, and so on. The version number which appears in the preamble is only the exception. It always takes 4 bytes. The encoding algorithm WebAssembly uses is called libass-wasm, short for Little Endian Based 128. It can encode up to 128 2 to the 7 unique values per byte. So for unsigned integers, any value from 0 to 210 is a single byte, and for signed integers, -6. We'll avoid writing a full implementation of LEB-128 right now, but there's a trick we can take advantage of. For non-negative integers that fit in a single byte, no encoding is necessary. True. That means 2 to the 8. Yeah, because it's 8 bits, right? Oh, stop thinking. Give me the answer. Oh, okay. Okay. All right. Guys, I'm going to have a break in 2 minutes. I'll be back. In fact, I think I'm going to stop streaming now. Gotta do some laundry, and then I'll be back. Now we're going to read more about section. We can now handcraft the module with the section required to define a function. Nope, blank bytes. Flat infinity. Oh, that's why we do it. Type section, section identifier, section size in bytes, number of entries that follow. Type section, entry 0, type function. Empty parameters, empty vectors, return values. Section identifiers, section size in bytes, number of entries that follow. Got it. Another. Okay. So zero. Okay. I think like an empty block return type. Range reserved for type construction form separate from opcodes. Not really. Okay. Awesome. Awesome. Guys, we'll see each other soon. I need to take a rest. I need to take a break.